To a lesson of Dr. Pell. Let's take a look at the idea of adding up an infinite number of terms in a geometric sequence. For instance, suppose that we're crossing a room and we decide to first go halfway across the room. Then let's go half of what's left. 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 And so forth. Half, 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 half. Look, notice that we're getting closer and closer. If we were to add up all the possible halves that we could get, notice that we would have crossed the complete room. If we would have gone through this process an infinite number of times, all the way through, we would have gotten one whole room, which means that 1/2 plus a 4th plus an 1/8 plus a 16th and so forth forever is equal to 1. Let's think about that for a minute. Okay, so let's look at this geometric sequence and see if we can use our geometric summing technique to find the sum and verify that it actually yields 1. How would we do this with an infinite number of things? Well, let's try it. Okay, remember what it was? We take the first term that we're adding. It's 1/2. Then we multiply by a fraction. Now this involves what we need when we go from term to term. What are we multiplying by as we go from term to term? We're multiplying by 1/2. So let's do that. We have a 1/2 raised to the number of terms. The number of terms is like infinite, but let's just keep going for a second. -1 divided by 1/2 minus 1. Okay, so taking a look at this, let's think. The number of terms is going to get big. What happens to 1/2 to a number raised to a number? Let's just call the number n perhaps. As n gets really, really big. Well, let's kind of look at this for a minute. We can distribute the power of n, or the exponent, across the division. So that'll look like 1/2 to the n. Now think about 1/2 to the n. So we're taking 1 and we're dividing it up into 2 to the n pieces. How big is each piece? Well, extremely small. So like 1/2 to the n is a very small number. And as n gets bigger and bigger and bigger, this guy right here gets smaller and smaller and goes to 0. So as the number of terms goes upward, this guy right here goes down to 0. So if we're looking at this infinite sum, pretty much what we do is, in this particular case, because 1/2 to a big number goes to 0, this part vanishes. So our sum should be obtainable. Let's see. We have a 1/2 times -1 divided by quantity 1/2 minus 1. All right, let's look at that. Because the other part over here was 0, vanished. So this is what we're left with. Now on the bottom, 1/2 minus 1 is -1/2. So we have -1 over -1/2. Now, that negative, we could just make a positive here. This is like 1/2 times 1/2. The 1/2s would cancel and we'd be left with 1. Or if you don't like that, let's think of it this way. 1/2 times 1/2. Now, if you say 1 over something, it's like taking its reciprocal. So you could think of this as 1/2 times 2, which then you could say is 1. Or you could just multiply top and bottom of this fraction by 2. See, that cancels. Again, you get the same thing, and you get 1. So indeed, it does work. We can find the sum of an infinite of an infinite geometric sequence. At least when our common ratio number, like 1/2, has the property that when we raise it to a really big number, like, and when n is really big, that goes to 0. Now, perhaps we wouldn't be able to do this if this wasn't true, so we probably should check this before we say that we actually can take the geometric sum and figure out what it is. Because if this doesn't happen, maybe we wouldn't be able to take it, and maybe it would be unobtainable. Thanks for watching.